of the materials itself. If we start with the most important case, which is the case of the so-called long fiber reinforcer, we usually have in mind the basic element with which the component is then fabricated, which is the so-called lamina, the single lamina, in which we can allocate a single layer of fibers surrounded by the matrix. Role of fiber and matrix, I'm not going to repeat it because we have already said when we started to talk about ceramic matrix composites. And the convention that is usually used is to define a principal material coordinate system on the XYZ axis, and the longitudinal axis, that is the x-axis equivalent, which has the same direction of fiber alignment. This is usually called axis number 1. When we go in the orthogonal direction, that is in the transverse, that is orthogonal to the fiber direction, this is called axis number 2. Sometimes it's the y-axis. And when we go through the thickness of this single lamina, we have the z-axis, that is the axis number 3. Please remember that we are talking here about fiber, apart from the special cases which are used with metallic matrix composites, like, for example, silicon carbide on tungsten or silicon carbide on boron, etc. We are talking about something which has an average diameter from 10 to 15 microns. So this means that, and please remember the concept that we already studied of critical volume for the single lamina. We are talking about a thickness of a single lamina which is not exceeding, just to have an idea, the double of the diameter of the fiber, that is 30 microns. But when we want to fabricate a component, we can have some millimeters up to 1 centimeter or more, that depends of thickness. And so this means that this basic element, which is used to model the mechanical behavior of the composite materials, is just one, and we need to refer to a layered concept. That is, we need to overimpose one layer on the other one, and then we can change the orientation and so on. We will see that in order to fabricate the components having the desired thickness, which is defined in the design step of the component itself. So we have usually a principal material coordinate system, which most of time is denotated with 1, 2, 3 axes along the fiber direction, orthogonal to the fiber direction, and through the thickness of the single lamina. So this means that this system is an anisotropy, and this result in mechanical behavior properties or characteristics that are quite different from those of conventional alloys, isotropic alloys. Why? Because if we have in mind anisotropic materials, think, for example, to an aluminum alloys belonging to one of the class which is used for aerospace application. If we apply, in the case we have in front of us materials with an isotropic behavior and normal stress, we can think to a tensile stress, but the same applies also in compression. In compression, the standard answer of the materials is extension in the direction of the stress And then we have a contraction in the orthogonal, that is perpendicular direction. But we do not have, in the case of isotropic materials, shearing deformation in this case. And it is also true, let me say, the opposite situation, that is when we think to apply a shear stress, that is a tangential stress, tau, not sigma. And when we apply a shear stress to an isotropic material, this is going to result only in shear deformation, but no extension or contraction in any direction. And in this case, with this modeling, as we will see in a moment, we do have only two materials properties which can be considered independent and which are necessary to quantify the deformations. For example, we can have the Young modulus and the Poisson ratio, because we know that from the Young modulus and the Poisson ratio, we are able to estimate or to calculate the shear modulus, which is the third parameter. So we can have, as known, Young and Poisson, and then calculate the shear, or Young and shear modulus, and then calculate Poisson, all the other, the remaining combination. But just these two materials properties are independent and are necessary. When we move through the class of non-isotropic materials, what is going to happen is that this is not more true. And if we apply a normal stress, we can have obviously extension, for example, and contraction, for example, but also shear deformation are going to arise. And so we have a coupling, and this coupling between both loading modes, this applies also in the case we apply shear, okay, in terms of deformation modes of the materials itself, is also called shear extension coupling, which must be taken into account when we are going to model the behavior of the materials if subjected to a load. To be more clear with respect to what we have just said, this is the case of an isotropic material. So you see, if, for example, like in this case, we apply a tensile stress, we do have, you see here, an extension here, but we do have also a contraction, and we are able, in the case we have a linear elastic behavior, like those which is modeled by the Hooke law, we are able to calculate the deformation of the materials itself in the direction of the load applications. And then through the Poisson ratio, μ, which is reported in this second formula, we can calculate, knowing the Young modulus, we can calculate also the contraction of the materials. This in the case we apply a normal stress. Again, if we are having in front of us the isotropic materials, but we are going to apply a shear stress, that is a tangential stress, again, under pure shear loading, since we have said that we can expect a pure shear deformation, this means that we can easily calculate by the equivalent Hooke law applied in the case we have a tangential force operating on our system, the shear deformation. And then this shear deformation can be put in relation with the Young modulus by knowing the Poisson coefficient of the Poisson ratio. And we do not have, as you can see here, elongations in the classical term, which are referred to deformation along the x-axis or along the y-axis. This is a case of a shear stress applied on the plane xy in a general coordinated system, but the same applies also if we are thinking here to apply a normal stress along the y direction or along the z direction, or here for the shear in the plane xz or in the plane yz. This is the isotropic, okay? And so you see here that we have three constants. I mean, we have the value of the Young modulus, the Poisson ratio, and the shear modulus. But, and if you look here, that's clear, by the so-called Lamé equation that we have already studied, we can calculate one of the three missing, so we have two independent parameters. In our case, in the case of lamina, if we follow our, let me say, definition of the principal material axis, we are in a special case of non-isotropic materials, which is also called orthotropic materials. So the single lamina reinforced, please remember, now we are discussing about that, by long fibers, it belongs to the class, in terms of mechanical behavior, of the orthotropic materials, which are characterized, as it is evidenced in this drawing, by three mutually orthogonal, that is perpendicular, planes of material symmetry. And in this case, the axes 1, 2, and 3, defined as we have defined it, that is, thinking to fibers which are oriented in this way, they are also called as principal material directions. And what is going to happen in this case, and this is our case? Well, if we subject an orthotropic materials to a normal load, like in this fourth case, but a normal load which has the properties to have the same direction of one of the three principal directions. Here it is represented the direction 1, but the same applies also for the direction 2 or for the direction 3. Well, if we apply a uniaxial tension along one of these three principal material direction, well, the orthotropic materials behaves just as an isotropic materials. That is, we can have only extension and contraction, non-shear deformation. Only extension and contraction, non-shear deformation. And in this case, we can write very similar equations to those we have defined before for the isotropic materials. That is, we can calculate easily the principal deformation strain along the the axis number 1 by dividing, and that is using the Hooke law for the linear behavior, by using the applied stress and the Young modulus in the direction 1. Then we can calculate by using the Poisson ratio, which refers to the plane 1, 2, because we are thinking that the load is applied along the direction 1 and the contraction on the plane is happening in the transverse direction, that is here, which we have defined like direction number 2, in a similar way, but with a different notation of what we have defined for this isotropic case. And the same applies for what it concerns the case in which we are going to apply a shear loading, a pure shear loading, along the principal material axis, that is on the plane 1, 2, or on the plane 1, 3, or on the plane 2, 3. And again, as you can see here, the shear deformation can be defined by the ratio between the applied tangential stress, the shear stress, and the shear modulus G12. If we then move to the case in which, and this applies for orthotropic materials as well as for generally anisotropic materials, we are going to apply, let me say, a normal stress, like in this case, or a shear stress, like in this case, but or for anisotropic materials or for orthotropic materials, that is our lamina, with the hypothesis that the stress for the orthotropic materials has no the direction of one of the three principal material direction, that is no along axis number 1 or axis number 2 or axis number 3, but it is applied on a direction forming an angle, a general angle with the principal material coordinate system. Well, in this case, we have tension, so we have axial deformations, contraction, for example, that is transverse deformation, but you see here also shear deformation are going to arise. And the same applies in the case we apply a pure shear loading, but not on one of the principal planes, okay? And in this case, we have shear, but we have also normal deformation. That is, we have strain along the axis X and Y. And by knowing the Poisson coefficient for the XY plane, the contraction of the material in the Y direction. You see, here we are using XY, and then it will be also Z for a coordinate system which is not the same of the principal material system. And then we can calculate by using the shear coupling coefficient eta, which is reported in this formula, as you can see, also the arising shear deformation. And with the same concept, if we apply a pure shear loading, apart from the calculation of the shear deformation, by using the shear coupling coefficient, we can calculate also the axial deformation in the two directions, which are not the same of the principal material direction, Y and X and Y. So this is the basic that we must remember when we are going to discuss about mechanics of composite materials, because in the case we are going to study as a fourth case, and that is the case of long fiber reinforced composite materials, which are the most performing in terms of structural behavior, most performing composites that we can fabricate. We have in front of us an orthotropic behavior of the single lamina. And another matter will be to discuss how the laminate, that is the sum of different lamina which are requested for the fabrication of our thickness, will behave. But if we start for the single lamina, let me say we can also introduce another important concept, which is obviously, and again, linked to the heterogeneous nature of the composites we are going to discuss. That is the approach of the mechanical modeling, which will be limited to the linear elastic behavior of the constituent, as we will see, can be the approach can be qualified in two different, let me say, terms. The first one is the so-called micromechanics approach, and the second one is the so-called macromechanics approach. What does it mean? It means that when we are going to follow a micromechanic approach, we want to study the behavior of our single lamina by taking into account the interaction between the constituent materials that are the reinforcement phase and the matrix materials, by having a look on what is going to happen at microscopic scale. That is, by having a look on what is going to happen during the interaction between the fiber and the matrix. Instead, if we follow a macromechanics approach, we want to study the composite materials, let me say in this way, how, as in the case we are going to use an equivalent materials, so thus presuming that the lamina is a sort of homogeneous and the materials and the effect of the constituent materials are detected only as averaged upper and microscopic properties of the composite materials. So this means that in order to define overall parameter for our lamina, for example, the modulus, as we will see in the one direction, or the modulus in the two direction, and so on, and the same applies to strength, and thinking that this is a sort of homogeneous materials, in order to define a macromechanic approach, we can try, and this is our aim, to understand what is going to happen at micromechanical level, so defining some basic equations with which we can predict, for example, the macromechanical properties of the materials itself. And this is very interesting and very important because if we start from the micromechanics, I mean, we can try to design the interaction between the two different phases, the fiber and the matrix, depending obviously on their single properties, in order to design a lamina showing a macromechanical properties, which is the property desired by the designer of the composite materials. The basic equation, the basic question of a lamina macromechanics are what are the characteristics of a lamina and how does a lamina respond to applied stress as a wall. Instead, if we move to micromechanical level, we are going to ask what is going to happen when we combine the fiber with the matrix to have the lamina, and so which and how it can be estimated, which are the expected properties of the lamina, taking into account the properties of the single phases, the fiber and the matrix. If we should have in front of us, so let's go behind again, anisotropic materials, there is another concept that we need to remember. Usually when we discuss about stress and when we discuss about strain, we take as reference the case of an uniaxial application of the load. And we have always written, for example, the Hooke law in the form stress equal to young modulus multiplied by the strain, having in mind a fixed direction. But we should remember that even though we are thinking a lamina in this case, so we are in a sort of plane stress conditions. That means we do not have stress on the z direction, because we are thinking that an applied load can be applied or on this direction or on this direction, but not on the perpendicular direction. So this means that the stress along the z-axis, as well as the other shear stress having the notation of the z-axis, like reported in this slide, they are 0. We should always remember that an overall, let me say, description of the behavior needs to remember that we must approach this problem by a tensorial notation. This means that when we are discussing about strain, we should take in mind the possibility to have strain along the x-axis, strain along the y-axis, or shear strain on the plane xy. Corresponding to the application of stresses which are a normal stress on the x-axis, a normal stress on the y-axis, or a shear stress on the plane xy. And the relationship between this vector and this vector in the tensorial notation is made or is mediated, as you want, by a matrix which for an isotropic materials is those reported here by bracket, and which fully describes the simple cases we have previously defined. So we have, as you see here, the notation is between the strain and the stress, not like I wrote here. We do have in the first term of this matrix, which is just the reciprocal value of the Young modulus, which allow to us to write the Hooke law in the x direction. And then we do have also only the three parameters we have mentioned before, apart from the Young modulus we have already mentioned now, but also the Poisson ratio and also the shear modulus G. This is the situation in plane stress for anisotropic materials. If we move in the case of anorthotropic materials, like in our case, and we are discussing here about the applications of a plane stress in the principal materials direction on that plane, we do have a similar approach of the previous one. Again, we have a vector of strain, we have a vector of stresses, but we need to introduce values of Young modulus which are different according to the direction, longitudinal direction, like this one. This is a case in which the x-axis is equal to the axis number 1, the y-axis is equal to the axis number 2, and the z-axis is equal to the axis number 3, according to our previous notation, because we have a different behavior, I will tell it to you, if we apply a normal stress here or a normal stress here, that is along 2, along y, and we need to specify the values of the Young modulus along the related direction. Again, as you can see here from this approach, in the case in which we apply a load in the principal material direction, we do not have any shear coupling effect, according to what we have said before. But in this case, we do have 4 constants which are requested to us in order to make calculation, in order to make modeling, because we have the 2 values of the Young modulus, one on the 1 or x direction, one on the 2 or y direction, and then the shear modulus in the direction x, y, or that's the same direction 1, 2, and then the Poisson coefficient. Being possible to calculate from the value of the Poisson coefficient yx, the value of the Poisson coefficient xy, since it is valid, this equation, for which from this, by multiplying the ratio between the 2 Young modulus in the 2 x and y direction, we can calculate the other Poisson ratio. We should say that in the first case, we have 3 parameters, elastic parameters, this one, of which 2 are independent. In this case, we have 5 elastic parameters with 4 which are independent among them. Micromechanical. So let's go a little bit inside, having made this introduction for what it concerns the differentiation in terms of behavior of isotropic, orthotropic materials and anisotropic materials. Well, if we would follow, let me say, a pure micromechanic approach and a pure macromechanic approach, of these 4 parameters you see here, now we are going to use the notation which refers to the principal material direction. In a very pure macromechanical approach, it should be supposed that these 4 independent parameters would be known by performing direct experimental characterization of the unidirectional lamina, that is by laboratory testing. But what we want, and this is the purpose of the micromechanic approach, is to understand if we are able, as I told to you before, to have an estimation of these macromechanical parameters by looking to the phases, matrix, reinforcement, which are going to be used for the fabrication of the single lamina, the geometric properties of the single lamina, and the properties of the single materials, that is separately taken, the properties of the fiber and the properties of the matrix itself. And this is the object of the micromechanics that we want to discuss a little bit in order to have a link then with the parameters which can be used for the macromechanic approach, which is the approach used for the modeling of the response of many lamina, one on the other one, in order to put one on the other one in order to form our laminate, that is our component having a specific engineering thickness. So we are going to consider our fiber, we are going to consider our matrix. For example, we know, which is the Young modulus of the fiber. We know which is the Young modulus with some hypothesis that I will tell to you now of the matrix. We know how much, then I will be more clear, are the quantities, volume essentially, of fiber and volume of matrix which are used. And our question is, can we have an estimation starting from the geometrical configuration, starting from the properties of the single phases of which is the modulus, and then we should say in which direction, but we will see it, of the composite materials? Well, if we make this question, we are going to discuss about micromechanics of the single lamina and micromechanics of our basic element for composite materials. Let me say that all what we will say from now on is subjected to some assumption, that is to some hypothesis, which to some extent, that depends on the system we have in front of, can also represent a sort of inherent limitation. For example, the first assumption that we make is that we have a perfect bond between fiber and matrix. This could not always be satisfied, but all the theory that we will see, if this point is not true, the theory is not valid. So our first assumption is that the bonding between the fibers and the matrix is so-called perfect. That means that the matrix is able to transfer the load to the fibers without any damages or without any rupture at the interface between the fiber and the matrix. Another important, let me say, hypothesis that we make is not reported here, but we already discussed it before, is that the single component, they do have a linear elastic behavior. And this is the second one, this is the first, this is the second one. And the third hypothesis is also that the single phases, that is the fiber or the matrix, when considered alone, they show an homogeneous and an isotropic behavior. So these are the main assumptions that are, let me say, made in order to write down the prediction equations. Let's go before looking to how this prediction can be made to some preliminary conclusions. The preliminary conclusions is that if we follow this approach, starting from the properties with this hypothesis, from the properties of the fiber and the properties of the matrix, we do have quite sufficient, quite accurate prediction along the direction number one, that is the direction of the alignment of the single fibers. And this implies also the estimation that we can make for the Poisson ratio in the plane 1, 2. But let me say, prediction on the transverse direction, that is the direction number 2, which implies also, obviously, the shear modulus G in the plane 1, 2, are less accurate. And so they have been developed also some semi-empirical approaches in order to have better estimations in the transverse direction. And what we will say and what we will see are the so-called alpine side relationships, that they are called semi-empirical, that is, they can request also lab testing in order to define some coefficient which are present in the alpine side equations in order to have a better accuracy prediction for the transverse direction. That's the conclusion. Now let's go inside. So what we want to do essentially, and this is the objective of the micromechanic approach, is that if we are thinking about elastic modulus or stiffness or compliances of the composite, we would like to define a sort of equation for which we can define the, let me say, moduli, the stiffness of the compliances, of the composite materials, knowing the value of the elastic modulus, the Poisson ratio, and the volume fraction, that is the quantity of the phase of the fiber, and at the same time of the matrix. As you can see here, if we use this general formulation that we will be then defining in a very simple way, in the case of the fiber, but the same applies also in the case of the matrix, we are just defining one value of the Young modulus, one value of the Poisson ratio. The same applies also to the matrix. So we are making that hypothesis that we told before, that if considered alone, hypothesis number 3, the single materials, the fiber and the matrix, must respect the behavior of homogeneous and isotropic materials. The same approach in terms of micromechanics, if it is referred to an estimation of the strength, also, let me say, wants to define simple equation for which we are able to define the strength of the composite materials, starting from the strength of the fiber, starting from the strength of the matrix, and having in mind the relative quantity, that is the volume fraction of the fiber and of the matrix. The equations that are written down with a micromechanical approach, they respond to this general scheme. And these are the complete hypotheses which must be satisfied in order to be sure that the micromechanic approach, with a limitation in the transverse direction that I already told to you, can be used. Some of them we have already defined, that is homogeneous, linearly elastic, isotropic, for what it concerns the fibers, homogeneous, linear elastic, isotropic, for what it concerns the matrix. We have to add some other hypotheses. That is that the combination of fiber and matrix also give rise to a linear elastic behavior of the lamina, macroscopically homogeneous and orthotropic, as we said before, without initial stress value, that is stress-free at the beginning. Then the matrix must be void-free, and the fibers, and this is very important, apart from the perfect bonding we already mentioned, they must be put inside the single lamina in a regular way. That is, they have to be regularly spaced and perfectly aligned according to the direction that we defined before. So one could ask, well, these are very, let me say, relevant initial hypotheses. Well, the answer is that for the practical application and for the practical way in which we actually realize our composite materials, even because we can have a degree of freedom when we use a number higher than 1 of the single lamina, these hypotheses can be considered more or less respected, essentially with a limitation, I repeat, of what is going to happen in the transverse direction, essentially when we have materials, composite materials, which belong to the class of polymeric matrix composite materials. For example, that is in the most common cases, in the case in which we have a thermoset matrix, like epoxy, for example, and a reinforcing fiber, high-performing reinforcing fiber, which can be glass, which can be, for example, carbon, which could be, generally speaking, silicon carbide, which can be also Kevlar. And in these cases, this hypothesis can be assumed as responding to the real behavior of our component. The same, with a little bit complication due to the formation of a network of cracks, is also, let me say, true if we are going not to design a weak interface. In the case we have ceramic matrix composites. Essentially, the linear elastic behavior can be considered respected. Plasticity effect can arise in the case of the metal matrix composites, which are actually outside our field of discussion, because looking to the application, as I said to you before at the beginning, this is the class most commonly used in aerospace application. When we use this approach, the resulting let me say behavior is usually plotted by very simple conventional diagrams, in which we put on the y axis here the property of the composite materials, for example, the Young modulus in the one direction, the two direction, the strength in one direction, the two direction, and in the x-axis, the quantity of the fiber volume fraction, dF. So this means if we use this approach, and here we have, for example, VF equal to 0, and here we have VF equal to 1, that is 0% of fiber, 100% of fiber, and this is not more the case of a composite materials, but this is the case of the monolithic matrix, and this is the case of something made only with materials which report the fibers. We start from the value of the property of the composite materials, which is equal here when VF is equal to 0 to the matrix value, and is equal here when the BF is equal to 1 to the fiber value. And then we do have the behavior when the fiber volume fraction is going to be increased. In this way, usually the properties resulting from the micromechanic models are reported. So let's start with the first one now, and taking our unidirectional lamina, you see here. Now we have again our standard notation of the principal material axis. And let's think that we want to define a simple equation to estimate the Young modulus in the one direction, that is in the direction of the alignment of the fibers, this one, knowing, these are our assumptions, the value of the Young modulus of the fiber, the values of the Young modulus of the matrix, and the respectively defined volume fraction. Here we have the hypothesis that we had done, how we could, let me say, think to approach this problem. Well, this is our lamina here. We have our fibers, you see, these are the fibers, okay? So we applied a load, a total load on the longitudinal direction. We make our hypothesis, and among these our hypotheses, there is also the fact that we can use the hook law, as we have said, and the bonding is perfect. We can expect, if this load is distributed all over the cross section here, because this has a thickness, obviously, okay, we can think two things. The first one is that the load, not the stress, the total load, which is supported by the composite materials, will be partially supported by the matrix and partially supported by the fibers. But the second, which is the most important in order to understand how we can proceed, is that the strain of the matrix is equal to the strain of the fiber, is equal to the strain of our composite, Because if this situation would not be respected, this means that we have not more a perfect interface, a perfect bond between fiber and matrix. And so we can make this isostrain hypothesis, for which when the interface is perfect, that is, there is a perfect bonding, the strain in the fiber is equal to the strain in the matrix is equal to the strain of our composite. We are talking about longitudinal strain, okay? Now, we have said that we can use the Hooke law for the two components. So we can also write that the stress in the fiber is equal, obviously, to the Young modulus of the fiber per the strain in the fiber. That's the same, the Young modulus of the fiber per the strain in the composite, since this condition is going to be considered valid. And the same also for the matrix, okay? So the stress in the matrix is equal to the Young modulus of the matrix multiplied by the strain in the matrix, that is, the Young modulus of the matrix multiplied by the strain of the composite, being, also in this case, epsilon m equal to epsilon c. And now, since what we have to sum, they are not the stresses, but are the forces, the total load, which is applied to the composite, is resulting from the load which is supported by the fiber and the load, summing them, which is supported by the matrix. That is, we can say that the stress in our composite materials, and we are talking about the direction number 1 in this case, multiplied by the area of the composite materials. What does it mean? We have a cross-section which is made like this. So we have our fiber here, okay? So we have a total area here of the cross-section, which is the area of our composite materials. And then we have also here the area AM of the matrix, as well as the area AF of the fibers. And so the area of the composite is just the sum of the area, total area of the fiber and total area of the matrix. So we can write, according to a linear elastic notation here, that the load, which is PC equal to the stress in the composite multiplied by the area of the composite, is equal to the sum of the forces which are resulting by the stress which is present in the fiber and the stress which is present in the matrix. And so if we divide this expression per AC, we get this final expression, okay? Remember what we have said before. But this final expression, that is AF, divided, for example, by AC, if we take as a reference something which has a thickness of 1, but the same applies also if it is then, if it is 10 or 15 or 20, it doesn't matter. That is, we write AF multiplied by 1 divided AC multiplied by 1. And this means, being 1, this unit length, that this ratio AF multiplied by 1 divided by AC multiplied by 1 is the total volume of the fiber divided by the total volume of the composite, and is exactly what we call percent of fiber volume fraction, VF. And the same applies in the case we are going to discuss about this term, which will give rise to the percent volume of the matrix. And so this is, then if we move to not to absolute value of percent, absolute value of volume, but to percent fraction, this means that Vm plus Vf it's equal to 1, or if you want percentage, is equal to 100%. So we can also write that Vm, for example, is equal to 1 minus Vf, and vice versa. And so that equation that we have defined before is going to be result in this expression. And if we divide, because we have the Hooke law, that is stress equal to Young modulus multiplied by the strain. If we divide this expression by the deformation of the composite, the strain epsilon c, we can say that the modulus, it is called also longitudinal modulus, that is the same of A1, okay, of our lamina. So in the one direction, you see here, it can be estimated by knowing the Young modulus of the fiber, the Young modulus of the matrix, and the percent volume of the two. This is in the longitudinal direction. It is also called rule of mixture, or approach void, as you want, limit. If we are going now to discuss what is going to happen in terms of representation, of graphical representation, as I told to you before, you see here the diagram is quite simple, because we start from the values of the Young modulus of the matrix. We finish to the Young modulus of the fiber, and this is just a very simple linear relationship which can give to us in the one direction an estimation of the Young modulus of the composite materials, depending on the fiber volume fraction. But thus the increase is a linear increase by increasing the fiber volume fraction. And if you remember what we have seen before and said many times before, I mean the first slides with data, since in our situation we do have that the Young modulus of the fiber, they are sensibly higher of the Young modulus of the matrix, thanks, for example, to a combination of epoxy, and look the data in the table, just say with carbon fibers, for example, or silicon carbide fibers. This means that the Young modulus in the longitudinal direction is strongly influenced by the fiber modulus with respect to the influence of the matrix modulus, only because the value of the fiber, of the Young modulus of the fiber, is sensibly higher than those of the matrix. Also in this case, if we want, we can let me say, make some very simple calculation that, for example, define which is the fraction of the load which is carried, which is supported by the fibers when we apply longitudinal testing, longitudinal stress tensile in the one direction. And we have these final, very simple equations which tell to us, obviously, that the load is very strongly supported by the fiber. And this is obviously, let me say, an increased contribution, which is going to be increased when we increase the volume fraction of the fiber, which makes us, I don't know how to say, let me say, happy, because the fibers that we use inside this kind of matrix, they do have, yes, as we said, values of Young modulus higher than those of the matrix, but they do also have a very, very higher resistance with respect to mechanical resistance, the tensile strength of the matrix. And this is at the end the reason because of we say that the fibers are the reinforcing fibers, because you see, by using the fibers, depending on the quantity, depending on the volume fraction, we are going to increase the properties of the poorer matrix, both in terms of modulus as well as we will see, in terms of strength. Okay, this is what we already said before. If we move now to the transverse direction, that is to the direction which is orthogonal to the fiber alignment, and we make, let me say, the same approach, that is, we apply a load here, P, to our composite, our lamina. What we can say, and this is the basic, let me say, consideration with which we can make our calculation, is now that we have not an isostrain configuration, but we do have an isostress configuration. That is, the stress which is applied on the fiber is the same which is applied on the matrix, and it is the same which is applied on the composite. And so if in the previous case, that is in the isostrain, we were summing the loads of the fiber and the loads of the matrix, here, since the stress are the same, we can say that the total deformation of our composite is made by the sum of the deformation of the two phases considered alone. That is, the fiber and the matrix being true, the assumption that we have the same stress, that is, we are in an isostress condition. And so, simply, again, by using a linear elastic approach, we can define as a standard configuration. We have also written that the deformation is equal, the strain, is equal to the ratio between delta L divided by L. We can make it, and we can specialize this expression for the composite. We can make it for the fiber. We can make it for the matrix. We can apply the condition because of the total variation of length is given by the sum of the variation of length of the two phases. And so we are in the isostress case. And then with very simple calculation, we can use again the concept of volume fraction and the concept of the Hooke law with the Young modulus, and have the estimation by a micromechanical approach of the reciprocal value of the longitudinal modulus, what is called transversal here, by knowing again the fraction value of the fiber, the fraction value of the matrix, and the Young modulus of the two homogeneous material constituents. This is called also, in the isostrain, we have the point limit. In this case, that is in the isostress, in the transversal, this is essentially the reciprocal of the rule of Miser, is called also the Reus limit. And so in this way, at least for what it concerns the moduli in the direction 1 and 2, we do have an estimation by a micromechanical approach. Well, what is going to happen? Then we can plot it. This is an example, again, of the same approach we saw before. That is, we are going to move for the estimation of A2 from the value of BF equal to 0 to the value of BF equal to 1. What is going to be seen, and generally speaking, we do have qualitatively variation of the modulus E1. Sometimes it is written like in this case E11, but this means we are in the uniaxial direction 1. The same applies for E2 or E2. which give to us, starting from the initial value of the initial components, and a value or predicted value of the modulus, Young modulus in 1 and 2 directions, depending on the volume fraction which is used, and which are reported in this way. E1 is always higher. We can eliminate these 2 points because we do not have composite here. Essentially, we have pure matrix and pure fiber. E1 is always higher than E2. And if looking to the experimental data, the estimation of E1 made by the Voigt limit, well described if the hypotheses are respected, what is going to be experimentally measured. What is seen, and is that if we go to the estimation of A2 with this approach, you see here, these are the experimental data point, and this is the approach by the isostrain Reus limit. This value of E2 is calculated in this way, a sort of underestimation of the real value of the Young modulus in the transverse direction of our composite. And this is not good for us because we are thinking about materials for which we want to have the possibility to maximize the performance of the materials, and so we would rely on models which would be, let me say, which would have, let me say, a sort of acceptable error, which is not the case. And so this requests to us to make some modifications, and these modifications are those which we will discuss under the Alpine-Tsai approach, which I mentioned before, just to eliminate by a semi-empirical approach these underestimations. We can make the same approach for the determination of the Poisson ratio and of the other properties, including also the strength, but I think that for today we can stop, and we will start from this slide in the next lesson, which will be next Wednesday, so we can start the topic and we can complete it. And for today, I have finished. So if you have questions, please ask to me.
Prof.
Eccoci.
Volevo chiederle quest'ultima cosa che ha appena detto. Per quale motivo in questa seconda tecnica che abbiamo applicato viene sottostimato il modulo di Young?
Perché in realtà le ipotesi che vengono fatte, che sono le stesse fatte nella valutazione del comportamento in condizioni di carico normale, diciamo, cioè sulla direzione 1, sono ipotesi un po' forzate, perché lì poi la sezione che è più fortemente sollecitata è quella dell'interfaccia, e quindi spesso e volentieri fare un'ipotesi di interfaccia perfetta che rappresenta il vero e proprio anello debole, questo è uno dei motivi. Non risponde proprio a realtà.
Ah, ok, va bene, grazie.
Yeah. Any other question? Okay, so let's see again, and let's meet again on next Wednesday. Bye bye to all.
Arrivederci, prof.
Arrivederci.
Arrivederci.